So it is 0.00384 into 2 into 5 into what is rho. Rho is 820, that is the density of the fluid. The density of the fluid divided by what is mu. Mu is equal to 10 raised to minus 2 Pascal second. What is this coming? 0.00384 into 2 into 5. Sorry, there is a mistake. It is it is 5 into 10 raised to minus 5 into 820. Okay, so 2 into 5 into 820 is equal to this, okay, into 10 raised to minus 3. So it is coming as 0.0314. Just check the calculation once more. Yeah, this is the answer. Okay, so this is the Reynolds number. So the question number 8, if I go to the question, calculate the Reynolds number of this problem. So this is 0.0314. okay, so this is as far as the important assignment questions is concerned. So then we'll move ahead and see what are the other questions. Okay, fine. So let me go to the assignment problems again. So we have solved question number 7, question number 8, and we have solved question number 1, 2, 3. Let me go to the next question. Okay, so question 3. Okay, so what it says that consider a spherical particle of diameter d of mass m moving through a fluid in one direction under the action of a centrifugal force. Okay, so the particles is moving under the action of a centrifugal force. Okay, so let me draw it for your benefits. So I have a fluid mass, I have a small particle of diameter dp, okay, and the particles is moving because of a centrifugal force. So assume r to be radius of path of particle and omega to be angular velocity in radian per second. So the particle is rotating in some path. Let's say this is my path of the particle where it is rotating. Okay, so the particles is rotating in some path. 1 minute. Fine. So this blue line is the path of the particle. Okay, and this is the center of my particle, and this black is the particle which is moving. So it says that the radius is r and it is moving with a angular velocity omega. Okay, and the characterization of the particles is same as the earlier problem. It has the diameter dp, radius of the particles as ap, mass of the particle m, density of the particle rho p, density of the fluid rho, and the dynamic viscosity of the fluid is the same, and it is moving with a constant velocity. Okay, so it's rotating at a constant angular velocity. Okay, so what is the tangential velocity? Linear at any point. So the constant velocity u in this case is equal to r into omega, and it has some centrifugal acceleration. Okay, and this centrifugal acceleration of the particle centrifugal acceleration or the centrifugal force which is acting on the particle, centrifugal acceleration is equals to r omega square. Fine. Now this is the main problem. So there the external, in the previous problem the external force was gravity. Now my external force is the centrifugal force. Okay, so because of the centrifugal force the particles is moving in the fluid. Okay, that means it's rotating at a constant angular velocity around a circle. Okay, about a circle. So now okay, what will be the different forces which we talked about in the previous problem in this case? So here so this is how the schematics looks like in this case. Okay, so there in the previous problem the acceleration due to gravity was g. Here the acceleration due to the centrifugal force is r omega square and the velocity is r omega. Fine. So what will be the equivalent gravity force which is acting in the problem? Okay, so the body force, the external body force acting on the particle is equal to simply m into acceleration due to the external body force. Let me write it as external. ext. So what is the acceleration due to the external body force? R omega square. So it is m r omega square. Okay. The buoyancy force, so this is basically, I will write it as FE. FE. Okay. FB. What was the definition? M by rho p is the volume of the particles into rho is the displaced mass of the fluid times the external acceleration. What is that? So this is m rho by rho p into simply r omega square. So that means the FB, the buoyancy force which is acting on the particles, is m rho r omega square divided by rho p. What is the drag force which is acting on the particle? FD will be the exactly same. It will not change because it has some velocity. Okay. So when it will move with the constant velocity u, which is the same in this problem, which is r into omega, the drag which will be experienced by the particle will be the exactly same. The formula will be the same. So it will be, that means for that instant where its velocity is u, the drag force will be 6 pi mu u ap, as simple as that, is equal to 3 pi mu u into dp. So let me, I think these are the three questions they asked. Yeah, the force of gravity acting on the particles, that means the here it's mean to, it's trying to say that what is the equivalent gravity force which is acting on the particles, or the equivalent external force. It is m r omega square, as we have derived now. The buoyancy force acting on the particles is this, m rho r omega square by rho p. Yes, and the drag force acting on the particles will be the exactly same. It will not change. Okay. So these are your question number 4, 5 and 6. So what question number 4 says? Question number 4 answer is m r omega square. Question number 5 is m rho r omega square divided by rho p, and the question number 6 is 3 pi mu u dp. Okay, so I have solved all these questions. So let me then try to attempt the last question. what it says, a sphere of diameter 0.1 millimeter. Okay, so dp is equal to 0.1 millimeter 10 raised to minus 4 meter, and the radius of the particles is 5 into 10 raised to minus 5 meter. Fine. Density rho p is equal to 2.8 gram per centimeter cube. That means 2.8 into 10 cube kg meter to the power minus 3. Okay, is allowed to settle under the action of centrifugal force such that the acceleration, which is r omega square, or I will write it as acceleration is 50 g, where g is the acceleration due to gravity. So I will call that acceleration as a. Okay, a is equal to r omega square equal to 50 g is equal to 50 into 9.81 meter second to the power minus 2. Fine. The density and viscosity of the liquid in which the particle settles. Okay, the density and viscosity. So what is rho? Rho is equal to it is 0.996 is equal to 996 kg meter to the power minus 3, and mu is equal to 0.00801 poise. So 1 poise is equals to how much Pascal second? Anyone know the relation? So 1 poise equals to 0.1 Pascal second. So that means it will be this much of Pascal second. Fine. Okay, so this is how it looks like. I just quoted the data now. So what is the terminal velocity of the particle? Can someone calculate what is the terminal velocity of the particle? What is ut? Two rho p minus rho g, which is the acceleration, it will be a, okay, into ap square divided by 9 mu. What is that? 2, what is rho p? 2800 minus 996 50 into 9.81. Into AP square is 5 into 10 raised to minus 5 square okay divided by how much is this? This is the answer 0.6137 if I am not mistaken. Calculate the terminal settling velocity of the particle in SI unit. So you have to check it, okay, whether I have done it wrong or right, but this is how I think it will be. Yeah, so one last question is there. Calculate the parameter k used to ascertain the regime of the particle settling. I think first you have to calculate the parameter k and then use the proper formula. So this is according to Stokes settling velocity. Okay, this is the Stokes terminal velocity. That might not be the right answer. Okay, this is terminal velocity based on Stokes track. So first you have to calculate the parameter k, which is discussed in the lecture. Okay, that is for you to do the job. I will not do that. And then use the proper formula to calculate the terminal velocity. But this is based on the Stokes terminal velocity. Okay, it might not be the correct answer. So if it's fall in the Stokes regime, then this is the correct answer. But if it is not falls on the Stokes regime, if it falls in the Newton's regime, then you have to calculate it. So yeah, so this is how I'll in the next week we'll meet again at 3 o'clock. Please join. Okay then, bye. See you on next Saturday.